If p is greater than or equal to 1, then we want to show that the infinite sum from 1 to infinity of 1 over n plus 1 times the pth root of n is no larger than p. So if p is equal to 1, then we simply have, first we take the finite sum. Then we will let n approach infinity of 1 over n plus k plus 1 times k. That is equal to k from 1 all the way up to n of 1 over k minus 1 over k plus 1. Right? Partial fraction. Same thing, double check. K plus 1, k minus k. Exactly the same thing. That is equal to 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus all the way up to 1 over n minus 1 over n plus 1. So negative half cancel with the half. Negative third cancel with the third. Negative quarter cancel with the next plus quarter. So what's the pattern here? So obviously we have previous pair, next pair. The latter of the previous pair cancels with the former of the next pair. Right? So this former of the previous pair cancel with the latter of the previous pair cancels with the first one of the next pair. Right? But this one still stays. And so we have this one still stays. So that is equal to 1 minus 1 over n plus 1. Then we let n approach infinity. That is equal, the limit is 1. So in other words, when p is equal to 1, our infinite sum is equal to 1. Right? So we have equal sign. So when p is strictly greater than 1, can we still turn it into a telescope series? That's the question. Now, it's not that easy, but still doable. Still, let's look at its finite sum. K from 1 all the way up to n of 1 over k plus 1 times pth root of k. Right. So let's look at this general term. That is equal to, I'm going to rewrite k plus 1 into the pth root of k plus 1 to the power of p, then times the pth root of k to the power of p. Right, that is just k. Now I have to multiply by k to the power of minus 1 just to cancel it out. Right, still the same thing. And still times the pth root of k. So that it's still the same thing. Right. So in other words, now what do I have? So simply I have just this is what k to the minus 1. 1 over k to the minus 1, just k itself, right? So k to the power of 1, pth root, so 1 minus 1 over p, right? Times 1 over. So here I want to split it into partial fraction. And that is the pth root of k to the power of p minus the pth root of k plus 1 to the power of p. Right, simply, this is because this is just k plus 1, this is just k. Right, still 1 over k, still 1 over k plus 1. Right, still we have common denominator, k times k plus 1. we have k plus 1 minus k, still have 1. So this still the same thing. Right? Now it seems getting more and more complex, but it's okay, because in the end we can make it simpler. So here I'm going to construct a function called f of x. F of x is equal to x to the power of p. Right, so therefore f prime of x is equal to p times x to the power of p minus 1. Here I just assume that p is strictly larger than 1. So according to Lagrange mean value theorem of differentiation, f of a minus f of b is equal to, as long as it's continuous and continuous over closed interval ab and differentiable over open interval ab, then we have this following identity equation: f prime of c times a minus b, and c is in open interval. So I'm going to choose a equal to one over the pth root of k plus 1. Right, I'm going to choose b equal to 1 over the pth root of just k. So therefore a is smaller than b, indeed. All right, so to write this down, I have f of a. I'm going to plug this into here, right? So I have 1 over the pth root of k plus 1. If I switch this and that, and also switch a and b, still the same thing, right? So fb minus fa. So I have 1 over the pth root of k to the power of p minus 1 over the pth root of k plus 1 to the power of p is equal to f prime of c. P times c to the power of p minus 1 times b minus a. Right? 1 over kth root of pth root of k minus 1 over pth root of k plus 1. Right? So therefore, where is c? C is in this open interval AB, right? So in other words, c is greater than 1 over the pth root of k plus 1 and smaller than 1 over the pth root of k. We need this part of the inequality. So because p is greater than 1, so p minus 1 is greater than 0. So we can just raise to the power of p minus 1 on both sides and maintain the inequality. So c to the power of p minus 1 is smaller than this raised to the power of p minus 1. All right, what is that? That is so k to the power of minus 1 over p, right? To the power of p minus 1. Right? So we're going to multiply this onto this power. Right, what do we have? K to the power of minus 1 plus 1 over p. Right? We have this inequality. So also because this part is already positive and p is also positive, and also k to the power of 1 minus 1 over p is still positive because 1 over p is smaller than 1, right? So the power is still positive. So the whole thing is still positive. K is positive. So in the end, we have this can be smaller than p times this, right? So what is this? This is actually equal to my general term, right? General term is equal to this. So let me just write it down. So in the end, I have this conclusion. 1 over k plus 1 times the pth root of k is it strictly smaller? Yes, strictly smaller than that. Strictly smaller than, copy down p. First copy down this. K to the power of 1 minus 1 over p. And since this is equal to that, so that is smaller than this. So I still have to copy down this p, right? And I have to replace c to the power of minus p with this, right? K to the minus 1 plus 1 over p. So copy down this. 1 over pth root of k minus 1 over the pth root of k plus 1, right? So let me just, k to the power of 1 minus p, 1 minus 1 over p, k to the power of minus 1 plus 1 over p, right? They can just cancel out, right? Becomes k to the power of 0. That is just 1. So that is equal to 1 times p times this, right? So p times this. So p. So my general term is strictly smaller than this. So this, again, looks like a telescope series, right? How? So this is equal to p times let me just, so this time my finite sum, right, this time, my finite sum, k from 1 to n of 1 over k plus 1 times the pth root of k. This time is no larger than, still copied on the p, right? P is taken out. And so I have first of all p minus q. So when k is equal to 1, I have 1 over p's root, 1 over 1 minus 1 over the p's root of 2. When k is equal to 2, I have 1 over the p's root of 2 minus 1 over the p's root of 3, right? And when k is equal to 3, I have 1 over 3p minus 1 over 4p. Right? So simply I have, in the end, I have 1 over np minus 1 over n plus 1p. Right? So simply this and that, they can just cancel. It's always the latter of the previous pair cancels with the former of the next pair. Right, so this. Right, so latter cancel with the former, latter cancel with the former, and latter cancel with this former. So this still remains. Right? This still remains. So that is equal to p times, that is actually smaller than p times just 1, because I have 1 minus some positive number. If I don't minus positive number, I become bigger, right? So this is no larger than p. So my finite sum is strictly less than p. If I let n approach infinity, I can say that the infinite sum is less than or equal to p, right? So in other words, if I let n goes all the way up to infinity, this can be no larger than p.